All right, welcome to another exciting day of ICAPS and CPAOR. For those that don't know me, my name is Daniel Haribor. I'm one of the co-program chairs, and I'm very fortunate this morning. I'm very happy to welcome you here to this keynote from Associate Professor Bistra Dilkina, who comes to us from the University of Southern California. So Bistra is a very influential researcher, actually, in our community, and she's the winner of many awards and prizes. Just last night, actually, I understand that she was the winner of the Best Paper Award at CPAIOR. So originally, my plan for doing this introduction was, I will make like a list of all of the many laurels that Bistra has accumulated over time. But then I realized we only have an hour. So let me instead tell you why I think Bistra's work is amazing. So Bistra's work is at the intersection of discrete optimization and machine learning. In particular, many of her works focus on the development of solvers, combinatorial reasoning techniques such as mathematical programming, planners, but where the combinatorial decision-making process is guided, by data that comes from solving real-world problems. So the applications of Bistra's works are many, but some particular focus areas are sustainability, such as biodiversity, but also urban planning. She's also published a number of influential multi-agent pathfinding algorithms, which is how I came to know and admire her work. I guess what I'm trying to tell you is that Bistra is a researcher for the moment. She combines traditional optimization techniques with emerging AI technologies. She is addressing the problems that we're facing at the moment as a society, and we're very fortunate. Actually, she has a foot, I would like to say, in each of the camps that we have here today, ICAPS and CPAOR. We're very fortunate to have her with us here today. Please join with me to welcome Bistra Dilkina.
Hi, everybody. Thank you so much for having me, and it's a great honor to be here and give the keynote. Thanks to the organizers for inviting me for this event. CPOR has for a long time been my home and favorite conference ever, and now I also get to see the ICAPS community, where I've also kind of started to put one foot in the door with some of the work that I've done in collaboration with my dear colleague, Professor Sven Koenig. But today I'm going to try to give you a kind of wide overview of the works that my research lab has done at the intersection of machine learning and combinatorial optimization. As always, I'm very ambitious with how much material I want to cover, because I'm super excited to share stuff with you, so some of it might go a little fast. And as was mentioned, today I will talk a lot about my methodological work, but I always wear like two hats. I really love developing novel algorithms and advancing the state of the art in solving technology, but I'm also super passionate about making real-world impact and solving problems with social good implications. So in my other life, I also do a lot of work on AI for sustainability. So today, I'm going to show you the successful integration of machine learning and combinatorial optimization. Both of these fields have had dramatic advances in the last decades, really improving the complexity of the problems that they can tackle, the performance, the variety, etc. However, they're really complementary to each other. They capture strengths at addressing different types of problems, ML being good at pattern recognition and unstructured problems, so more like system one type of problems, while combinatorial optimization being good at logical and mathematical formulations and reasoning, and really addressing more system two type problems. But combining the strength of those two paradigms can really provide the next step change in the kind of problems and complexity that we can address. And I hope to convince you that some first steps in that direction have been done, and there's many, many more to do. So my talk is going to focus in two directions. In the first one, the bigger part of the talk, I will show you how we can improve the solver methodology for combinatorial optimization by augmenting combinatorial frameworks with learning components. And in the second half, I will talk about how we can improve learning methods that are designed to make predictions about things that are integrating downstream into decision making by incorporating the combinatorial decisions into the machine learning pipelines. Okay, so I'm going to try to cover a few examples in both of these buckets. Starting with combinatorial optimization, given the audience, there's not much to convince you that combinatorial optimization is extremely important. There's so many real-world applications that involve decision-making under constraints and objectives with a wide variety of applications, from ride-sharing to energy to AI planning to planning critical infrastructure such as energy, water, and roads. So, but the combinatorial application domains keep on growing in size and complexity, constantly pushing the frontier of what's needed from solvers. And therefore, we also have to think creatively of how to also evolve our field of constraint reasoning and optimization. One particular setting that is very common in the real world is that we just don't have just any NP-hard problem that we need to address, right? So like from a theoretical computer science perspective, you might be thinking like, okay, we're designing algorithms for NP-hard combinatorial problems. Well, a particular company, let's say like Amazon, is not solving all the different types of combinatorial problems. They might be focused on scheduling their trucks to make deliveries, right? And so day after day, they have the same type of problem, but with different parameters, like different demands, different delays on the roads, different locations when things have to be dropped off. So it's really beneficial to be thinking about combinatorial solving as a distributional setting, where again, we are not only faced with kind of like the abstract NP-hard problem, but in fact, we have access to understanding what is the distribution of instances that our end user or client will need to solve. And once you're in that paradigm, you also can think about the fact that you actually might have historical instances of those from that same distribution, right? So Amazon has already been scheduling their trucks for years and years, and so you might have access to that. So once you put your mind in that perspective, then you can really connect to the machine learning community where, there you have rows in a table that are samples from which we want to extract patterns to learn for predictions. Here, our samples are actually NP-hard problems. So it's a little next level of what one might call a sample for learning, but that's exactly what we're going to try to do today. We're going to treat instances of NP-hard problems as samples from the historical distribution that we want to learn from. And why do we want to do that? Is because if we're able to leverage historical samples, then we can attempt to learn search policies that are tailored for that specific distribution of problems, as opposed to thinking of, on average, is my algorithm doing well? And so with that idea of learning strategies, what we're hoping to achieve is to get better performance than generic one-fits-all algorithmic framework that are by fitting to that specific problem distribution. And hopefully, if we're successful at designing these ML-guided policies and make them flexible enough that they can actually learn across different domains and specializing to those domains, we can also alleviate the need for hand design approaches. So in industry, often what happens is that if you have a specific problem that you need to solve over and over again, you invest into hiring an OR consultant or a planning consultant that develops some custom heuristics for you, right? But how good it would be if you actually can also leverage these existing ML frameworks and just plug some of your problems and learn a policy that works well. So much of today's talk is going to be focused on one specific subfamily of combinatorial optimization, in particular mixed integer linear programming, where we have a mix of continuous and discrete variables subject to linear constraints and linear objective. And although that may seem like a strong restriction, in fact, many real-world problems can effectively be modeled and formulated as MILPs. And in fact, MILP solving is maybe one of the most widely used kind of combinatorial reasoning technology in the world, with tons of papers and statistics and analysis showing the billion-dollar market value of those models. So in the recent decade, there has been actually a slew of successful research developments of thinking about how to integrate machine learning to help MIP solving. One of the first papers, actually in 2017, came from my group using learning to guide branching in branch and bound for MIP solving. Building on an even earlier work on a node selection in branch and bound. But since then, there's been successful applications of this distributional learning to guide algorithmic framework for MIP across many different paradigms, from the kind of complete tree search algorithm that's familiar to both the MIP community as well as the planning community. ML has been applied to guiding branching selection, node exploration selection, primal heuristics, etc., and also successfully applied to heuristic and local search methods, in addition to configuration and somewhere ensembling. So again, today I'll illustrate just several examples that my group has led. So one of the most successful heuristic or local search methods used in the wild to solve real-world problems is actually large neighborhood search. Large neighborhood search has been successfully applied both to integer programs, but also for vehicle routing planning, for supply chain, and so on. It actually pops up kind of like as a standalone hand-design heuristic in many different applications. What is at the core of LNS is that you assume that it's easy to find a feasible solution, initial solution, but it might be of very bad quality. So at that point, you would choose a subset of your decision variables, unassign them, or what's called destroy them, keep the rest of the variable assigned to their current values, and then re-optimize just that part of the search space where you have unassigned a small set of the variables, right? So what happens if, for example, if we have a mixed integer linear program and we unassign, let's say, 10% of the variables and we keep everything else assigned, now we have a remaining sub-MIP that only has 10% of the variables in it, right? So a much smaller one where you might be now able to apply branch and bound. LNS is usually used on problems where within 1 or 2 hours you cannot solve the problem to optimality, right? So the kind of the hardest of the hardest. And a key part that drives the success of large neighborhood search is how do we select these destroy sets, right? So that kind of determines the speed at which we're going to get improving solutions. And again, in all these application papers I mentioned earlier, that's where the crux of the contribution is. There's usually some kind of a hand-designed heuristic, understanding some kind of problem structure from which you design the neighborhoods, right? The neighborhoods that decide how you pick destroy sets. So this is a perfect opportunity for this machine learning perspective where, okay, we have a heuristic, making it better might have dramatic impact on the solver performance. Can I learn a model, an ML model that can help me guide this as opposed to designing it, a custom one that then for any new domain, I will have to start from scratch. So in 2020, we worked on the very first ML-guided LNS for MIP approach, and since then, there was like a series of improvement over these ideas. In particular, one of the key questions about how to train this machine learning for large neighborhood search is how do I find good training data? So what does good training data mean here is I want to first have labels, and labels are these very good destroy sets, right? So can I have an oracle to tell me what is, given a particular incumbent and a particular solution right now, what is the optimum destroy set that I could have had, even if it's hard to find, so that I can give it to my ML as a training set to then learn to imitate. So this is obviously hard, but a node result from 2003 comes to the rescue from Fischetti and Lodi, which define exactly this problem, and they call it local branching, where essentially they basically augment the current existing MIP with its objective and constraint with an additional constraint that says, well, given the current solution X star, flip at most k of the binary variables in it, such that you, again, optimize the objective. Well, at the end of solving this, you have exactly this. You have the perfect set of k binary variables that you can reassign such that it will give you the best local move, right? The best change in the objective function from what you had before. But obviously, solving this is solving a MIP of the same search space size as where we started from, so extremely hard. And so in practice, this is prohibitively slow to integrate into this LNS iterative framework where we're going to be calling this choosing a destroy set many, many times in a row. But what a team at Google DeepMind did is said, well, okay, this is great. We can collect this data offline, even if it's expensive to collect it, for a limited number of training instances, and then from there, train a model that we can then deploy at test time to new instances that are never seen. So they basically ran this local branching MIP across the distribution of instances. They found that best solution found by the local branching and used that in an imitation learning ML framework where they basically train a model to predict those values, those decisions of inclusion in the destroy set or not inclusion in the destroy set. Okay. One problem with this approach is that they're using a classification loss, basically a cross-entropy loss for each individual variable. Did I select it correctly, as my local branching solution told me, or I did not? However, critical realization, if you know anything about optimization with these destroy sets, is what makes a set good is the composition of variables. The variables are working together such that combined with the constraints that are binding them, to provide a good opportunity for a move. So I might have a good destroy set, but then I switch 2 or 3 of the variables with the wrong ones, and suddenly that destroy set is actually really bad. So looking at individual variables alone really is very limited in capturing that structural property. So that's where we came from, is understanding that this is actually a structure prediction. We really want to get that prediction of the set as a whole. And so that immediately connected to current existing advances in the machine learning paradigm with contrastive learning for structure prediction, which in recent years, between 2019 and 2021, has been proposed for in the context of image recognition and graph representations, focusing on the fact that, again, here, you're also kind of generated a bunch of pixels to produce an image, and you want the whole thing as a whole to be good. So in contrastive learning, the key idea is that instead of just having examples that you can have to imitate, instead you have both positive and negative examples, and you're trying to create a model that will generate solutions, in this case images, that are close to the positive examples, but as far away as possible from the negative ones, right? And so the key idea, again, is to try to find these positive and negative examples that look similar to each other and yet are different, right? So in these pictures, we both of them have like animal with eyes and nose and ears, but one is a cat and the other one is a dog, right? So here in the context of combinatorial optimization, instead of learning only from the best destroy set or only from the images of cats, in order to get like a cat predictor, we want to distinguish between good and bad destroy sets, and then use those via contrastive loss to improve the structural prediction of our model. The key thing is to figuring out how to find those positive and negative samples. So positive samples are somewhat easy. Usually they're the best destroy sets or examples you can find. For the negative sample, what you want is you want to have this kind of idea of a hard negative where you want to find bad candidates, which basically in this case destroy sets that will result in a very small or no improvement in the overall solution, but that look very similar to the positive ones, meaning they almost have the same set of variables selected to unassign, right? So where essentially this heuristic can get confused, right, by missing just a few of them. So with this in mind, we proposed this contrastive learning LNS approach. This work was led by my PhD student, Tawan Huang. And so here at training time, we're going to collect this offline data by, again, running this local branching and finding optimum and near optimum destroy sets. But once we get those, we're actually going to generate these negative samples. And the way that we're going to generate these negative samples is, again, looking for those hard negatives. We're going to randomly perturb small percentage of the variables included in that optimum positive sample, reevaluate to see whether what kind of move it results in, and if it's like really much worse than the quality of the move that's in the positive sample, we're going to keep it as a negative sample. If it doesn't result in a bad move, you're going to throw it away and keep on sampling until we get those hard negatives. right? And then we're going to plug in now this positive, negative training data into our learning with contrastive loss in order to get a model that predicts at the end a vector, right? Again, a structured output of decisions, which is of length n, the number of variables we have in the problem, essentially telling us should that variable be included in the destroy set or not. And we're going to plug this into our contrastive loss, which essentially is looking at maximizes the similarity between that prediction pi of x to the positive examples, in this case a vector A of 0, 1s that are our local branching optimum set, and minimize the distance between the predictions to the negative samples at the bottom. So what is our learning architecture for this? So here we leverage something that now has become kind of the bread and butter of ML-guided learning for mixed integer programming, which was proposed in 2019 by Gas et al., where we wanted to find a learning architecture that is both size and permutation invariant. Why is that important? In combinatorial optimization, we often have a family of problems, but we are not fixed in size, right? So I might have a little bit more tracks this week and a bit less tracks next week. Also, the identity of having track A represented as variable x1, in the next day it might be represented as variable x100, right? So it has to be permutation invariant. And the perfect permutation size invariant ML modeling architecture is graph neural networks. So how can we represent mixed integer programs as graph? That's, again, something that has been long-standing as a kind of a model in the constraint reasoning community, where we have the constraint factor graph, where on one side we have the variables, on the other side we have nodes for the constraints, and we put edges between a variable and a constraint if that variable appears in that particular constraint. So it's a very natural in the constraint reasoning community to think of a combinatorial optimization problem as a bipartite graph. And essentially, this bipartite graph becomes the graph on which the graph neural network runs, right? So it's doing this bipartite message passing, basically from the features of the variables to the constraints, from the constraints back to the variable. So with these two things in hand, the learning architecture plus our contrastive loss, now I can show you some results. So here we're comparing to branch and bound, which in this case is using skip as a solver. We're comparing to two non-learning variants of a large neighborhood search with random neighborhood selection and heuristic neighborhood selection based on the relaxation, to the two state-of-the-art ML-guided approaches, the imitation learning LNS from DeepMind, as well as a reinforcement learning version that came that same year. So in magenta, you can see our approach, which is the contrastive learning LNS, and you can see a dramatic improvement in the anytime performance of our solver, finding a better solution way, way faster than the state-of-the-art. Okay? So the way to, in addition to looking at this like kind of runtime to quality curves, we can also look at the area under the curve, which is basically capturing the anytime overall performance of the solver. In mixed integer community, that's called primal integral. In the MapF community, they have another name for it, like AUC and so on. But here, always the idea is we want to capture that area under the curve, the speed at which we improve solution quality. So again, we can see from this analysis that we have 26 to 69% better anytime performance, not over the branch and bound, but over the best state-of-the-art baseline, including imitation learning and reinforcement learning. So these are really encouraging and dramatic improvements, and we were so excited. And this idea of contrastive learning and really thinking about the fact that, again, all of these ML guiding tasks in combinatorial optimization often involve not a single classification, but some kind of a structural decision, made us think of this contrastive loss as essentially like an empowering hammer that we could use now to hit many different algorithmic nails. And that's exactly what we did. But before I go there, I wanted to also show that we then tested this model. Again, this is a graph invariant, a size invariant architecture, so we could apply the same model out of the box without retraining on domain instances of larger sizes. And so here, again, you see that our model has very good generalization performance, meaning that it keeps its advantage over the other methods, even on instances that are unseen in the distribution during training. So then we took these contrastive laws and we actually successfully applied to other algorithmic tasks for guiding integer programming, including partial variable assignment in the predict and search framework that I'll briefly show next, as well as guiding branching priorities. So what is the predict and search framework in MILP? This is a relatively a new proposed heuristic method, which basically instead of like LNS selecting variables to destroy, what it does is it just does a one-shot reduction of the MILP problem. You can think of it as like, I guess some people even call it like a distillation. So we're going to predict a partial variable assignment, assign those variables, and then do search over the rest of them. Obviously, if our partial variable assignment is not very smart, we might now could possibly have cut off all the good solutions in the search space, so we can have arbitrarily bad solutions. So it's really important then to have good methodology of choosing those partial assignments. So in this Han et al. Paper in 2023, they proposed to, first of all, build an ML model that would do the partial assignment prediction, but then couple that with an expanded search space where they add this trust region where they say, well, to allow for mistakes but by the ML prediction, we're going to allow for up to K changes of those partial assignments during the search. So it essentially creates a trust region around that partial assignment that was proposed. So it expands, it doesn't fully relax it back, but expands the search space more than just assigning strictly a partial assignment. So they used imitation learning again in their framework. And so we said, well, OK, this is great. Again, we are doing a structured prediction where we're doing a vector of possible partial assignment recommendation. This is totally appropriate for our contrastive learning realization. And so again, the key thing here was to think about how are we going to design this positive versus sampling, positive versus negative samples data collection strategy. And in order to do this, we defined two types of negative samples, samples that are result in partial assignment that actually make the problem infeasible, which are really bad, right? You don't want your partial assignment to cut off all solutions. But again, they have to be hard negative, meaning they have to look very similar to the very good partial assignments, right? So we again do that by random sampling offline until we find good examples. And then we also want partial assignment that are similar to the very good ones, but actually result in very low quality solution, not infeasible, but very low quality. And so for that, we actually design a novel minimax optimization problem. So here again, you can see results on two domains, vertex covering combinatorial auction. In all our papers, we have more domains than that. I'm using this as running examples. And again, we compare our method in magenta, as well as in blue, to the existing ML-guided baselines, predict and search with imitation learning, neurodiving, we just did the partial assignment with ML, but without the trust region, and branch and bound. And again, we see 58 to 70% improvement over the best SOTA, including the ML ones. So this story can seem to repeat, and here I'm going to give you the third example, which is making branching predictions. So again, we use, again, contrastive laws in order to guide our training of an ML model that is, again, predicting a vector of 0, 1s for all the variables and saying which variables should we prioritize for branching during our branch and bound search. And the really nice part about this is that, first of all, it doesn't compromise the completeness of the branch and bound method because it's just a soft suggestion about branching priority. Second of all, it's done only once at the top of the search tree, so it's not like some of the earlier work on learning to branch where you have to call the ML model inside the search tree at every tree node, thinking about which variable to branch on next, which has a big overhead and often doesn't scale to large problems. So here we have like a one-shot branching prioritization and then give that suggestion to the solver. So here we are actually doing an improvement over Gurobi, which is much harder than improving over Skip. Obviously, Gurobi is the commercial strength solver that has been optimized for decades and is it's a leading solver in the industry. And so being able to report that with this we're able to improve the runtimes by 9 to 27% is, again, a huge feat for us. And again, you can see that performance in both the in-distribution small size on which we're collecting the training data and the out-of-distribution larger size where we might not be able to collect the training data due to the size of it, but the model still extrapolates. And the last point I want to make is you can see that the speedups on the right are actually of our model over Gurobi, which is kind of the red line in the middle, are really on those hardest instances, the one that takes the longest for Gurobi. So which is exactly what we want. We don't want to speed up the easy ones. We want to speed up the slow ones. Okay, so I hope I have convinced you about the usefulness of contrastive loss as a unifying ML framework for ML-guided MIP search across these 3 domains. Okay, so we've seen this like individual success within different verticals in terms of algorithmic tasks, for branch and bound with branching priority, to local search with LNS, to heuristics with predict and search. But can we do something more synergistic? So many of the current research improvements, including our own, have really focused on tailoring to specific domains and specific algorithmic tasks that we want to improve. Recently, there's also been some work on improving the ML-guided methodology across multiple domains. But in this work, which is actually my PhD student, Jun Yang's Best Paper Award at CPOR this year, we actually looked at can we start by creating a model that's able to learn common embeddings that are good across multiple tasks as a first step of really thinking about setting the framework for a foundation model for guiding ML-guided MIP solving. So the idea is that we're going to leverage this bipartite and neural network architecture for specific tasks that we've done before, but we're going to interject in between the prediction for the specific algorithmic task and the outputs of our graph neural network, a common ML MILP embedding, right? So we're going to try to get these common MILP embeddings to serve all of these different algorithmic tasks with a few layers of like specialized processing after that, right? So during training, we're going to be training across the training data from many algorithmic tasks by keeping by propagating gradients back to the MILP encoding such that they can serve all of them. So at this point, we keep the output layers, those specialized layers for the tasks fixed, trying to get the common embedding to be as useful as possible across the different tasks. And then after the fact, as a second step, we fine-tune those task layers to use these now frozen MIP embeddings to just get those final predictions for the task at hand. So these tasks at the end could be one of the tasks that was already using during the training, or it could be a brand new algorithmic task that we have never seen before. So in this, to evaluate this framework, we used already our existing work, leveraging some of the really hard to compute offline training data for backdoors and predict and search. So we have 3 tasks: backdoors, predict and search, and configuration. And so we're going to use 2 of those tasks for pre-training and 1 of those tasks possibly for a test time. So these are the sorry. So here we are comparing across this the 3 possible setups, given the fact that we have only 3 tasks for now. And often people are like, why didn't you do more? Well, again, collecting training data for all these experiments is solving NP-hard problems many, many times a row. So I feel sometimes embarrassed thinking about the energy footprint that my group has on given the fact that I work on AI for sustainability. But we've used tremendous amount of compute time. So here again, you see the comparison between training an ML model for just that specific task, like in the papers I showed you before, in the predict and search, just training with the predict and search data, specialized model for that domain, for that task, and we compare it to the results we get by this pre-training with for the MILP embeddings with the multitask model, and then fine-tuning it just for that task after the fact. So on the left, we see when the predict and search is the new task that was not seen during training, which means backdoors and configuration were the pre-training tasks. And we can see that the multitask-led model actually has a much better performance, in particular when generalizing to larger instances that are bigger than the training data. And we see the same idea of this like better generalization and robustness of the models over the other two tasks, configuration and backdoor. So these were extremely encouraging results, giving, again, 7 to 88% improvement over branch and bound across many algorithmic, well, three algorithmic tasks and multiple domains. So we are hoping that this is, again, a positive step in the direction of thinking about, like, can we create models that are able, that are pre-trained to compute these embeddings that then will reduce both the sample complexity, meaning how much additional training data we need for new tasks, as well as the performance, meaning the actual accuracy of the predictions that the models make for new tasks over time, and hopefully new tasks and domain in a foundation model, which extrapolates across both. Okay, so this is great. And so the interest in machine learning guided mixed integer optimization has really, as I said, kind of growing over the last decade. But one thing that has been plugging the community that I'm sure is very familiar to the CP as well as the planning community is benchmarks, right? And in particular, this idea of distributional settings for optimization, as much as it makes so much sense, and when I talk about Amazon and so on, everybody's yes, 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 of course that's the case. Nobody has really been releasing distributional collections of instances. So when we started, we were like really in a conundrum of like, where do we find data to show that this thing works, that has benefit? And so, and many others were in the same shoes. So a lot of the work so far has focused on either using, oh, I'm on the wrong slide, sorry. I got out of, so I'm just gonna go to what I'm talking about now. I'm gonna go back to the next one in a second. Is either using heterogeneous data sets, which kind of defeats the idea that we are trying to, so the whole thing about ML models is that they see patterns in data. And to see patterns in data, there has to be some kind of a distributional tightness, right? I mean, if it's like all over the place, there's no patterns in data, right? So if you use heterogeneous instances, then ML maybe can give you some advantage, but you're really tying its hands. So the more you have like real, like kind of a tighter distribution of problems, the more the ML might be able to use like really a specialized policy. On the other hand, in terms of distributional benchmarks, people have used like synthetic generators, but every single paper uses different parameters, like for vertex cover, different sizes of the graph, different density, blah, blah, blah. And so that basically ties the hands of apples-to-apples comparison, and just the whole idea of only evaluating in synthetic problem domains is somewhat problematic because, we know from the SAT community, for example, evaluating and optimizing solvers for random SAT is not a very good idea because you go to, let's say, verification instances and completely different things work well. So we've designed this distributional MIPLIP where we put a lot of effort in collecting the existing synthetic generators and domains. We have a collection of 8 domains and growing with generators and like standardized train test data sets, as well as across different levels from easy to medium to very hard. But what I'm most proud of is the 5 real-world domains that we have integrated into this library, where we worked very closely with other researchers in the field to try to share with us real-world distributions, including things from supply chain, last-mile delivery, as well as in energy. So if you're thinking about problems in this space, please check it out. Now I'm going to go back to the slide that I missed, which is this idea about whether so far, everything that I've shown you is obviously in the distributional setting, but sometimes we might not have historic data. So it's a natural question to ask, well, can ML help even in a zero-shot setting where we have no instances? So this would basically imply an on-the-fly learning to somehow help us guide the MIP search. And given the fact that we already had this very good success with large neighborhood search and guiding the heuristics there, we looked at this setting in the LNS framework. And so we recently proposed a solver called Balance, bandit-based adaptive large neighborhood search for MIP solving, where we're combining adaptive LNS for MIP, which basically is an approach where they have many, many different neighborhoods for selecting destroy sets in MIPs that have already been proposed, But we are now proposing to dynamically manage this selection of which neighborhood to use at every iteration of LNS using an online learning policy. And specifically, we are leveraging multi-arm bandit algorithms, which are ideal for this kind of online sequential decision making. Like I have to choose a neighborhood now, I do something, then I have to choose a neighborhood again, and so on. And so for this kind of zero-shot setting, we show results on individual instances, averaging over individual instances from MIPLIP, some of the hardest instances of MIPLIP. That's why we're calling them HMIPLIP. And so here on the left, you can see the performance of all the different variants of LNS which use a single neighborhood across this portfolio. We tried each one of them individually with different destroy set size, different strategy for choosing, and these are like the best ones that we found. On the right, you see the results of actually doing this online learning with the multi-arm bandits, which incorporates all of the neighborhood choices, but it has to, on the fly, gets reward signals and adjust its choices. And so what we observe is that we can reduce by 50+% the primal integral over skip, but also any balance configuration is better than a single neighborhood LNS. And the final point I want to make is that if you're interested in trying this, we've actually packaged it really nicely in a available Python package, which you just do pip and stuff and you can use it, thanks to our collaborator on this project, Serdar Kadioglu from Fidelity Investments. So since we are at ICAPS, I wanted to also plug in some of the applicability of these to AI planning. In particular, I have done some work, again, with my colleague Sven Koenig on multi-agent pathfinding, which has applications in coordinating robots in automated warehouses, in traffic management, in video games, in drone swarms, and like as in many combinatorial domains, MapF has actually its own slew of solvers that have been designed specifically, right? So they're solvers that are based on tree search, that have optimality guarantees. They have heuristic searches, including LNS, that is some of the state-of-the-art there as well, and other variants like ECBS, prioritized planning, etc. And so our student Tawan Huang, which was actually co-advised between me and Sven, really bridged that gap, bringing some of these parallels between ML-guided MIP solving and multi-agent pathfinding algorithms to hybridize some of these ideas. And so in his thesis, he was able to show that we can design ML-guided approaches to guide branching in CBS, to guide node selection in ECBS, and to select neighborhoods in large neighborhood search for MapF. And in all of these three cases, we again saw dramatic improvements. In fact, often maybe more dramatic improvements than what we saw in MIP, parts due to the fact that the MapF solvers are not as optimized and commercial strength as, let's say, Gurobi or Cplex. And obviously, it was not just like take this and apply it. For example, for MapF, you don't have this easy bipartite representation and a graph neural network approach, so you need to come up with some different models. The timing constraints are very different. Often in MapF, you want to solve problems within 2 to 5 minutes. So you have different priorities in what it means to actually improve performance. So again, we had to think about different sets of learning. And so we, for example, used SVM as our ML methodology. We used curriculum learning in order to get data from smaller to larger instances, et cetera. So again, even there's the hybridization, but there need to be new innovation within that context as well. So I hope I have convinced you that there's impressive synergies that can be achieved between machine learning and optimization paradigms. These kind of synergies are transferable and useful across many combinatorial domains, from mixed integer programming to MapF, but also in routing and constraint reasoning. And we can, again, learn from each other as communities. I don't think we should be doing these things in silos. If you're thinking about ideas, let's say in CP, you should be reading the papers in MIP. If you're thinking about this in planning, again, looking at papers and ideas from others to cross-fertilize ideas. And again, this also applies across different algorithmic families, from tree search to heuristics to local search to just configuration. And one key point I want to make is in all this work, it's really about augmenting our algorithmic frameworks as opposed to replacing them. Early on, like with the, when the whole success of deep learning came about, pointer networks, deep networks, there was some excitement about like, oh, we are just like going to train deep learning architectures that are going to just predict the solutions of the problem. They're going to throw away the algorithms and just learn to solve the problems. And I really don't subscribe to that way of thinking. I don't think NP-hard problems are at least realistic, structured, large size will be solvable by pure deep learning architectures. So really leveraging our community's work on algorithms and augmenting it with ML is the right approach. And at the same time, we're also incorporating different state-of-the-art machine learning techniques, maybe even posing new challenges to the ML community. So I'm hoping through that synergistic stream of research, we're also going to advance the science and application of learning to optimize as a field. So I think I have only about 10 minutes or less than 10 minutes to quickly show you a little bit about the other directions of embedding optimization components in machine learning. So as you know, in many real applications, before we go to the decision making, we need to have the data over which we're optimizing. Often that data is not readily available, but it comes from some predictions or estimations that we have to do upstream, right? So the full pipeline really involves both predictions and optimization to solve the problem. So in particular, if you're thinking about stock market and making like deciding your portfolio investments even on a daily basis, you might first predict your expectations on future returns before you optimize your portfolio subject to your constraints of whatever diversification and so on. So often what happens in this kind of applications is we think of those two parts of the pipelines as separate problems. We take historic data about available data and observed return on investments. We formulate that as an ML. We train an ML model. We evaluate the ML model based on accuracy, like mean square error. Once the ML team is done, they pass on the model to the combinatorial optimization team. They take the predictions as is, and then they design some models to solve the decision-making portfolio design problem, right? However, what happens with this kind of siloed approach is that we're really losing the opportunity to integrate this end-to-end problem. In particular, often ML accuracy does not translate in optimization performance when we don't have enough data to make like these models that are 99.5 whatever accuracy, right? The moment we have noisy data, on average, maybe the model is good, but maybe it's getting exactly the critical stock prices wrong and completely throwing off the optimization downstream. Right? And similarly, downstream, if we're optimizing the quality of our portfolios with respect to the specific point predictions, then that optimum solution with respect to wrong objective coefficients, again, does not translate into real returns. So how can we take the understanding of this pipeline of predictions with decisions and integrate it into end fashion? Basically, we want to automatically shape the ML model's loss, not for accuracy, but for the decision, the quality of the decisions that come out of the full pipeline. So we call this decision-focused learning, and it was proposed jointly with Brian Wilder when he was a PhD student at USC, and my colleague at USC, Milin Tambet, that has moved since. So again, here we're going to be focusing on decision loss, meaning we're optimizing for the final quality of the decisions, not for the ML accuracy. But in order to do that, we need to integrate this full pipeline into our learning, right? So we want to, at every pass of our learning, we want to make predictions, run the optimizer, get the decisions, run the decisions to the true parameters, get the actual quality, and then get gradients back to our parameters to do it again, right? So how can we do this? First of all, again, we assume this distributional setting where we have these historic instances about both of the features, the true parameters, and the actual optimization criteria and constraints. And so if we train a model, then on at test time, we're going to get new instances where we are going to just have the features, let's say historic prices. We're going to predict the objective coefficients. We're going to optimize, and we're going to deploy, okay? The hard thing here is that we have a solver in this like training loop. In particular, this could be a combinatorial solver. So how do we differentiate and get gradients when we have this kind of solver in the loop? So in our first problem, we only addressed linear programs and submodular optimization. Some combinatorial problems can be reduced to LPs, the easier one, like bipartite matching and shortest path. So we thought that was a good start, and submodular optimization obviously is combinatorial in nature. So here we design a way to get these gradients. In particular, we leverage the idea that locally optimum continuous solutions must satisfy the KKT conditions, and we can actually differentiate through those equations at the optimum, the KKT equations. And in fact, this has already been proposed in the continuous convex problems, but the idea is, can we make this work also for LPs and submodular optimization? The challenge here is that when you have this kind of linear constraints, you can see that with a small change to your theta parameters that basically decide what are the objective coefficients of the problem, you can snap from one corner of the polytope being optimum to the other one, right? So we have this kind of discrete switch. So we introduced a regularizer to smooth things in order to be able to get gradients that are useful during training. So with this approach, we showed that in that first paper that we can achieve 15 to 70% improvement over this two-stage approach, which divides ML and decision-making across 3 different domains: matching, budget allocation, and recommendation. After that, we followed up with a real-world application where we worked with an NGO in India where they support patients with TB, which have to take pills every single day, and if they miss like more than K number of pills in a row, basically their treatment becomes ineffective, but every day they have only a very limited number of patients that they call. So they have to predict who are the patients that are likely to skip their pill, and then optimize the limited resources of calls to assign based on those predictions. And so here in this real-world setting, we were able to show that with this decision-focused learning, we're dramatically able to improve the final decision quality of these recommendations, although our ML accuracy is slightly lower, right? But we actually have this end-to-end constrained reasoning in the loop. Sorry, where did I go? Okay, so I don't know whether I'm going to have time. I have to wrap up. So I was going to show you quickly the fact of how we extended this to NP-hard problems. This was kind of unsatisfying, only getting to LP and submodular optimization. I really wanted to have MIP in the loop. And so this is a follow-up work led by my PhD student, Aaron Ferber, on MIP as a layer in a neural network, which, again, basically looks at how can we get these solver gradients for MIP problems. And during training time, we leverage the fact that we can use actually a cutting plane approach, which is not very effective as a solver at test time, but at test time, we can use regular solver, but here we use cutting plane, which results to finding an optimal solution by adding more and more linear inequalities to the problem until basically the LP relaxation of that tightened problem is itself integral, right? It gives us an optimum solution. But the beauty of doing that is that at the end, we have an LP whose optimum is exactly the IP optimum. So then we can leverage our already existing work on differentiating through the LP to get the gradients during training. So with this approach, we are actually able to now solve truly combinatorial problems with end-to-end learning. And we show dramatic improvements in both investment portfolios, matching, and energy-aware scheduling, where our approach gets much better quality than the two-stage approach. And also in orange, we see that just doing a LP relaxation does not actually work. So with this, I hope I've convinced you that decision-focused learning is another extremely interesting paradigm where we integrate predictions and combinatorics in an end-to-end fashion. So here we are not helping the combinatorial algorithms, but what we're doing is we're helping the machine learning algorithms to make better predictions in terms of parameters that will guide downstream decision-making. And so there's many other things that I missed in my talk, some of the things my group has done, but obviously, as I said, there's many more in the community. It's really exciting to see how many interesting directions there are. There's still many open questions about different applications, real-world impact, new algorithmic families. Scaling up to very large instances might require innovating on different architectures for learning, and so on. So I hope to see many of you follow up and do some of those innovations. And I would like to thank all the people and agencies and industry that has supported my group's research on this. Thank you so much.
Thank you, Bistra, for that wonderful talk full of insightful observations, inspiring ideas. We have some time for questions. Who would like to have the first question? Please wait for the mic.
So one of the very few examples that I know of an embedded machine learning model in a general purpose MIP solver is in the Express team, where they decide whether or not at the start, essentially algorithm configuration, whether or not to scale or whether or not to do local cuts. What are the current barriers in your opinion? And is there a clear missing link that you believe should be worked on that is stopping this wide scale adoption of embedded ML models in general purpose MIP solvers? Because for the most part, these things are usually handled by a if statement or two that then decide.
Very good question. Actually, I've been talking to people from Cplex and Gurobi or other solvers and also asking the same, why are you guys not following up on this? And they actually got really good answer in a sense that they can provide the hooks to do it, but at the end of the day, back to what I said, the benefit of these models is to training it on a specific sub-distribution that is client-specific. So the solver team doesn't have, it's not the team that's actually going to train the ML model that works for, let's say, energy scheduling or is working with a supply chain client. So they basically, the idea is that this actually has to be on the kind of consulting application team side, because again, both, I guess, the strength and the weakness of this approach is that it's not out of the box, you just general purpose, put it in and it's just going to work, right? You need the data that's specific to the application. And that's why I feel for example, if we start having some of these kind of pre-trained embeddings, maybe those things can be then integrated in this kind of overall solvers and then provide the hooks to fine-tune them for a specific client, something like this. But with the current approaches, they're very much reliant on get me data from this domain. And before you have that, you don't really have a good starting point.
Other questions? Try and take over here.
Thank you for the wonderful talk. You mentioned that in decision-focused learning, by learning the optimization problem objective, we can actually deteriorate the actual machine or the model that we learned in terms of the pure prediction. Mm-hmm. So is it possible that we go so far that we actually totally go off from the actual prediction, and although we get some maybe better results in the optimization problem, but the prediction is totally wrong? And what would it mean?
Yeah, good question. So kind of the interpretability of what the ML part alone is predicting sometimes can really become very black box, right? So it almost becomes a way where the objective coefficients predicted by the ML model are some kind of solver guidance, right? Biasing it towards the right decisions. So this is a problem. So in this setting, you kind of lose some of that interpretability, and also that means that this particular ML model is no good for, let's say, if you change the downstream optimization task, right? Because again, it might be actually really wrong on some parameters that maybe under the current constraint structure are not important. I always give this example. Let's say I might have a model where I'm predicting the delays in Los Angeles, which vary dramatically. Some things get really slow, some things get really fast. But my client is only interested in specific drop-off and origin destinations. Maybe they have restrictions in terms of what kind of roads even the trucks are going to go. You still want to use the whole data across the city because it provides additional signal, those other street segments. But in this end-to-end learning, it might really downgrade the ML performance on those because they never bind on the constraint side. So it's a challenge. So it's I guess a trade-off between performance versus interpretability. But this idea about the fact that, in a sense, this decision-focused learning is almost like providing an end-to-end solver is actually really, I think, maybe problematic if you care about interpretability, but also powerful in terms of like thinking of this as like combined solver. And in fact, the part of the talk that I didn't manage to give is like really taking these decision-focused learning ideas and using it as a solver for MI/NLP problems, which are much more complex than MIP, where we're essentially just using that ML plus solver paradigm to learn a model that takes the MILP, learns to predict linear coefficients, then learns like Gurobi or Cplex, and get solutions that end up being really good solutions for the overall MI/NLP problem. And I don't know if you're familiar, but like the state of the art in nonlinear integer optimization is much more poor than the state of the art in mixed integer linear programming. And so the solvers are really not good. So being able now to kind of leverage MIP solvers for these kind of applications is really powerful. And we actually have quite a good success with that in collaboration with Meta, looking at table sharding, which is kind of assigning recommender system tables to GPUs, and in photonic device design, which is for their VR program, where they're trying to create these like 3D printed devices where they split wavelengths into different beams, which becomes like this kind of electromagnetic nonlinear optimization problem. But it works very good as an end-to-end solver, essentially, for those settings. Sorry, I used this opportunity to pitch the stuff of the talk that I didn't give.
So we'll take one more question, I think, and then we'll break for coffee. Peter.
So you had this task-independent MIP embedding. Have you looked at it, and can you see any insights maybe from it, or is it just a bunch of random numbers from a human perspective?
We haven't looked at it much, mostly because, if we had so right now we are doing this for a single domain, right? So if we had multiple domains, let's say we had look at the clustering in this MIP embedding, then I could say, well, are the clusters in the embedding space kind of like aligning nicely with my understanding of like different problem domains of different problems? I don't have that here, right? I'm like having problems from the same domain, but I'm doing these embeddings for multiple tasks. So it was unclear of what signal we were going to be looking for to correlate with some kind of external index of meaningfulness. Right? I think as we progress of like expanding this into both across domains and across tasks, we're going to start getting more of that ability to actually, open that black box and look at whether it's generating something we can make sense of.
How cool was that? Didn't I promise you an amazing keynote? Please join with me to thank Bistra Dilkina.
Thank you.